Hey everyone, let's get introduced to the idea of a binomial matching network. So remember in the previous lecture, we talked about this notion of a multi-section matching network. So it was kind of like the quarter wave transformer where you had a single transformer term here with some line feeding it. Only now we're extending that to, say, n of these transformers. We also imposed that condition of small reflections, which allowed us to make some interesting approximations along the way. So just to recap, you have some gamma here looking down this entire system, which I'm going to write as a gamma there. So that's the net reflection coefficient seen looking down this entire cascade. And every one of these little segments we've assumed has a constant electrical length theta. We don't necessarily have to impose that condition, but that was one of the conditions we also imposed as part of our approximations to see if we could simplify the mathematics. And then at each one of these little discontinuities, there was a reflection coefficient, which we called the partial reflection coefficient. Okay, so there's one here, there's another one here, and so on, all the way out to the end. So that would be gamma 1, gamma 2, gamma 3, and then eventually you reach this gamma n. And the partial reflection coefficients would satisfy gamma sub n is equal to z sub n plus 1 minus z sub n, and then divided by z sub n plus 1 plus z sub n. So sorry, that's a little, here, let's draw that, z sub n. Okay, so the partial reflection coefficients. Now, what we also found was by the small reflection, the theory of small reflections, we found that we could write this net input reflection coefficient here. I'm going to write it as a gamma, as a function of theta, was equal to, I had gamma sub 0 plus gamma sub 1 e to the minus 2j theta plus gamma 2 e to the minus 4j theta plus plus eventually gamma sub n e to the minus 2nj theta. Okay, so you had this kind of like a Fourier series, and each of these little gammas was determined by the discontinuity between each of these steps. Okay, so you have this idea where the total reflection coefficient looking down this entire cascade can basically be approximated in terms of all of these individual little reflection coefficients. And what we found is this behaved a lot like a Fourier series. So if I wanted to impose special conditions onto this function, I just have to choose the appropriate coefficients accordingly. All right, so that's sort of the baseline here. Okay, so just in your mind, remember that theta here is an electrical length. Okay, so theta is equal to beta times L, where beta was 2 pi over lambda times some L here. Or equivalently, the frequency and wavelength, you could express this as omega divided by the phase velocity times L. So you can think of this theta as kind of a frequency-dependent term, but we've normalized it to the wavelength so that we're just kind of looking at this in terms of radians rather than actual raw lengths in any specific distance. So what this does is it creates an interesting effect where you can imagine, here is my gamma of theta. So this is like my frequency response. It's sort of normalized to some particular electrical length. So equivalently, you can look at this as a gamma of omega since they're just related. And down here, there'll be, let's see, this is my theta axis here. And I can impose some condition that makes this behave like a Fourier series, right? So it could do something like this if I wanted that particular frequency response. Or what I might say is I want to create some sort of passband. So I may get some function that does this sort of behavior, where there's some center frequency f naught here, and then maybe it does that kind of thing. And I have the freedom to shape this response by choosing n, the number of segments here, and the appropriate coefficients. Okay, so that's the idea you want in the back of your head. So when you see theta, think in your mind it can also be substituted with omega using some coordinate transformations here for my frequency response. Or if you don't like thinking about omega, think about it just actual hertz here. Okay, so you have f naught, theta naught, omega naught. These are all sort of proportional to each other, so it's equivalent to think of them all in these terms. And because we have this sort of finite Fourier series thing happening, what you'll have is this particular little segment of bandwidth, and then it's going to repeat over and over as I go up in frequency. So that's yet another one of those fun properties of the Fourier series, is for a finite number of terms, I will get a periodic function here. Okay, so with all that in mind, what is the binomial matching network? So the binomial says the following. Binomial matching network. Whenever you hear that, what we are going to impose, that should be a gamma, as a function of theta, I'm going to impose the condition that I want this to equal a times 1 plus e to the minus 2j theta raised to the nth power. So you see it's a binomial raised to some n number of powers here. Okay, so I'm just going to impose. I want this function to come out of this series here. So how do I do that? And why would I do that? So the first question is the why. So I'm going to underline that. Why would I want that? Well, one of the first properties is gamma of pi over 2 is equal to 0. So it's going to impose some matching condition at a particular frequency. Okay, because you can see if I just set all of this to 0, you'll basically find that 1 plus e to the minus 2j theta has to be 0 in order to satisfy that. And you find that this will occur when theta is equal to pi over 2, right? So we'll do that derivation real quick. So you have 1 plus e to the minus 2j theta is equal to 0. So e to the minus 2j theta is equal to negative 1. And that occurs when theta is basically plus or minus n pi over 2, right? Because I multiply that by 2, and then I'll get a negative 1 for my phase. And this will be, actually, I think you have to get every odd pi over here. So just don't think too much. So the point is that you'll get a 0 here at this particular pi over 2. So if my theta naught is pi over 2, I'm going to have a matching condition. So that's the first property we like about this particular function, is that it will match right there at the center. The second property that we're going to enjoy with this particular function here, so again, so the monomial, polynomial, binomial expansion. One of the fun properties here is also called flatness. Okay, so what that means is not only is gamma going to be a 0 here, but its first derivative is going to also be 0, and the second derivative, and the third. So if you actually take the derivative of this thing and evaluate it at all those same points, they will all be zeros. So this is something you probably were not taught in calculus, but when you have a function where not only is the derivative 0, but the second and third and fourth derivative, you get this interesting phenomenon of flatness. So just to sort of visualize, here is a maximum, or you could say a minimum of a function, where the derivative is 0. But if I also had the second derivative, you get this thing where it'll smush it out a bit like that. Okay, and if the third derivative is 0, then you might even squish it out even more, and so on and so on. So when multiple derivatives are all 0 at the same time, they smush out the little maximum or minimum here. So this thing has the property where we'll just kind of write it off to the side here, where the nth derivative of gamma, gamma of theta is also equal to 0 out to capital N derivatives. Okay, so that is good for a matching network because it implies not just some simple match, right? So a simple match you've seen might do something like this and then come back up again. But with the flatness, that little trough there gets smushed out, which means we're going to have very high bandwidth if we try and get our reflection coefficient to match this function here. Okay, so how do we make this expansion here match this particular function? And the answer is actually pretty straightforward. So let's go ahead and write that out now. Okay, so I've rewritten my expression here. So this is the Fourier series we get when we impose the theory of small reflections onto a multi-section matching network. And this here is the function I would like to try and create by choosing the appropriate coefficients here. So fun fact, you may have learned this way back in algebra, but if I take a binomial and I expand it out to n powers, you actually get a pretty straightforward expression. And it looks like this. The summation for n equals 0 to n, and you get c sub n choose n times e to the minus 2j theta. Okay, because you imagine I just do a FOIL on the first terms, and then I carry out the multiplications on the next terms and the next, and do this n times. You probably saw this a long time ago, way back in algebra. You may have even seen this when you did probability and statistics, but this coefficient here is called the binomial coefficient, and it evaluates to n factorial over n minus n factorial times n factorial. So the binomial coefficient. Okay. Okay, so this is just a property. If you expand that, it evaluates to this, where each of those terms comes out to here. So just dig way back into your memory hole, and you may have seen this identity somewhere. But you can also see here is a finite series out to n terms, and here's another finite series out to n terms. So all I need to do to create this function with all of its wonderfully desirable properties is equate the two together. So what you'll find is I need to impose the condition that gamma sub n is equal to a times c sub n, or little n. So the way you'd read this is n choose n. Okay, for the binomial coefficient. And so that's going to sound a little weird to say it out loud. So little n choose big N, I suppose. In MATLAB, there's actually a command called n choose k. And this is actually a function where you'd give it an n and a k, and it'll carry out this calculation here just with a k instead of the capital N. All right, so just remember, these coefficients satisfy this little expression here. So I just need to choose my reflection coefficients to match this property, and I will get this desirable little thing here in my frequency response. So how do I do that? Well, the answer is quite simple. I just have to choose the appropriate characteristic impedances along this line to create the desired partial reflection coefficients. All right, so remember, I have power over this by simply choosing the characteristic impedances. So let's move down here. So gamma sub n is equal to, remember, my partial reflection coefficient, n plus 1 minus z sub n, or z sub n plus 1 plus z sub n. And I just need this to satisfy a times little n choose big N. Right, so that now you can see, you have two choices, right? I can start here all the way at the end and sort of work my way back, because I can calculate this as a ratio, essentially, in terms of these parameters here, where I would use n plus 1 for the load, and then, let's see here, we'll try put it here. So I could start here at, say, big N plus 1, that would be the load, and the little n would be the final term, and I would work backwards. Or alternatively, you can imagine starting at the left end and working my way up. Okay, so you have these two fixed points at each end, and I have an expression that defines this one in terms of the one either to the left or to the right of it. So that's the idea there. Now, before you get carried away trying to perform this calculation, there is a little caveat or asterisk to that. And I'm a little frustrated at Posar because he very, very casually mentions this problem in the textbook here. And that is, if you actually try to do what I just said, that is, you start here, I use this left point as a fixed point, and I start solving for n plus 1 from left to right, you'll get a bunch of solutions for these characteristic impedances. However, if you then do the exact same calculation, but start at the right and work your way left, you get a different result. So it's not consistent whether you go left to right or right to left, which is not really good. And when you actually try and plug it into a reflection coefficient calculator, that is, if you calculate the reflection coefficient down this cascade, it doesn't quite satisfy the properties we thought it should. So Posar doesn't really talk about this. It's actually a mathematical problem that we've created sort of an over-determined system here. And he very casually just throws it away with like a simple comment. Oh, by the way, this isn't consistent, so really you have to do this other thing. So there are lectures online somewhere that explain this, and I had to do some digging to find that problem because it was very frustrating. I tried this and it didn't quite seem to work. And so it's a weird, obtuse mathematical quirk in the way this is set up. So what you do instead is you do an approximation to this ratio here. And so it's kind of like the Taylor series expansion of this function. And you actually get 1/2 times the natural log of z sub n plus 1 divided by z sub n. And then I set that equal to z sub n raised to the nth power. Now, I can do this, and this actually tends to work for a lot better, but we need to calculate what this a term is here. We've been kind of neglecting it for now, but you can think of it as a boundary condition on my system here, because there's a whole bunch of functions that will satisfy the property, but we need to scale this coefficient appropriately so that it actually satisfies what the physics of this problem here. So the way that's done in the book is they just say, imagine taking the limit as sig theta here approaches 0. Okay, so for very, very short wavelengths, it's as if all of these multi-section transformers squish down into nothing. And what you're essentially left with is an input line here with a load. So let's see if I can cover that over there, because I shrank all of these transformers down to an electrical size of 0. So the implication is that at 0 frequency, my reflection coefficient should simply be between my transmission line and my load. So what we're going to do, we'll come over here, the implication is gamma of 0 is equal to z sub L minus z naught over z sub L plus z naught. Okay? And at least in the limit as theta approaches 0, that's basically what you get. And this is going to equal, we're just going to plug into this term here, put in a 0 for theta, you see that goes away, and I just get 1 plus 1 to the n, okay? So you see I get 2 to the n times a here, okay? So now I'm just going to solve for a. This implies a is equal to 2 to the minus n times gamma L minus ZL minus Z naught over ZL plus Z naught here, okay? So I'm going to choose this particular value for that leading coefficient, and it will essentially satisfy the physics of this system here. Okay, so you can kind of think of it as a boundary condition on my left and right impedances here. So this is now just a constant that is independent of frequency that we can take for granted here. So now the question is, how do I solve all of this? So I'm going to now plug this into here, and you'll notice that I'm going to get 2 to the minus n times z sub L minus z naught over z sub L plus z naught times little n, choose big N. And now I'm going to apply that exact same little approximation here. So that ratio gave me this natural log here, so I'm going to do it again to this guy. And I will get 2 to the minus n times 1/2 times the natural log of ZL over Z naught. So this is an approximation over here. Then I'll get a little n, choose big N on the end. So you'll notice these are the things I'm trying to calculate. These 1/2s are going to go away here. So what you're left with is basically the natural log of z sub n plus 1 over z sub n is equal to, or at least approximately equal to, so let's put a little approximation here, approximately, like so, 2 to the minus n times the natural log of z sub L over z naught, c sub n. So all of this stuff here is actually a constant, independent of any of the frequencies or other terms. So let's just call that, I don't know, just alpha, c sub n to the n, like that. Okay, so that just represents these terms here. And so if I want to calculate this, I'm going to raise e to everything. So I got just almost enough space here. So what you'll find is z sub n plus 1 divided by z sub n is equal to e to the alpha little n, choose k right there, which finally gives me something like the following. Z sub n plus 1 is equal to z sub n times e to the alpha here. Okay, so there's my recursive expression. So I'd start here at, say, the far left, where zn is equal to z naught, and I would calculate the first term, and then I would use that one to calculate the next, and it goes all the way down to the end. And this expression here turns out to now give me a consistency. So the mathematics of this is kind of weird and clunky. And you notice we did like multiple approximations on top of approximations. And even this thing here was an approximation using the theory of small reflections. And then, okay, so now I'm approximating this little fraction here into this natural log, which I then approximated this into this, and I get this term here. So it seems weird and mathematically clunky, yet if you actually try this expression out, try this, you'll calculate all of these little characteristic impedances, following this little formula here for some load and some characteristic impedance with some number of segments, and you do the binomial coefficient, the n choose k, you actually try this out, okay, and you create a model for a matching network that satisfies that picture, and it gets surprisingly good results. It's kind of baffling to me how well this works, given how much hand waving went on into creating it. But so we'll do that in class. I'm going to actually write a function that calculates these impedances, and then we'll calculate the reflection coefficient given these values and talk about it. And it's surprisingly good. So I'm kind of baffled by it. It's kind of magical. So you'll have your pi over 2 here, like that. And this is my theta axis, and it goes out to pi before repeating again. And you see something that kind of does this, where it just dips down, it gets really flat, and then it wants to come back up again. So it's a really huge bandwidth. So this is my gamma of theta here. I'm taking the magnitude of that. So think of that as like my frequency response there. Okay, so again, it's kind of weird and magical. We had so many mathematical quirks and hand-wavy approximations that went into this, yet when you actually try it out, it works pretty well, and it doesn't even need that many terms, right? You can do as few as like n equals 4, and you get something that looks kind of like that. It's very bizarre to me. But there's some other practical issues we'll talk about as well. So you don't need like 15 or 20 segments in order to make this work. It does work miraculously well with only a handful of 2 to 4 of these transformer networks, and you get very, very good bandwidth. Okay, so that's the essence of the binomial matching network in a nutshell. So just to rehash, we had this multi-section transformer, and we imposed this condition here. I wanted my reflection coefficient to satisfy this function, and so I just did the expansion of my Fourier series here to match this binomial expansion here. And what I found is I had to create a condition where these were my reflection coefficients, which I then imposed by just artificially creating a bunch of characteristic impedances here, which remember I have control over, say in a microstrip line. These are determined by just how thick the width is on that top line. So I'm just choosing a bunch of thicknesses to create this reflection coefficient, and you just use this iterative calculation with some approximations, and you get this result here. So I just choose my widths of my microstrip, say, to get just the right characteristic impedances, which are imposing just the right reflection coefficients. And lo and behold, like magic, it actually kind of works pretty well. Okay, so that's why it's called a binomial matching network, because this is a binomial term raised to some nth power. And so you get this little guy here is my binomial coefficient. So that's where the term is coming from here. Okay, and it has the desirable property of being matched right there at the middle of my bandwidth, and it's flat. So you get this huge bandwidth around that matched value there. That's surprisingly pretty good. Okay, so there you go. So that's the binomial matching network. A lot of disgusting math to create an actually surprisingly simple result here. Okay.